This is the Calculus TA Training Selection Test for year 2026. We are required to solve this question. You can pause if you want to solve it on your own. Are you able to grasp the meaning of these questions? To solve this problem, we need to use proof by contradiction because it is far easier to assume the opposite and show that it is wrong. Let's begin. First one, we have to show f has no local minimum and local maximum. So first we assume that f has a local minimum at some point AB in R squared. And from the problem and from the description, we know that the second order partial derivatives after the second order are continuous, which means f is C2. So a point AB must be the critical point of f. And for critical points, we can use the second partial derivative test. For local minimum, there are two cases. The first one is this. The determinant is greater than 0 with fxx of AB greater than 0. Then we can determine it is a local minimum. And from Kirchhoff's theorem, fxy of AB is equal to fyx of AB, which means we can just swap the order differentiation because f is C2. Then we expand the determinant. So fxab times fyy of AB minus fxy of AB squared is greater than 0. And for convenience, we use star to represent this. Okay, but we know that fx's of AB plus fyy of AB is equal to 0, which means fyy of AB is negative. This further implies fx's of AB, fyy of AB is negative. So star is negative. And we roll before that star is positive, so it's a contradiction. The second case is that the determinant is equal to 0 because it is inconclusive, so this is also you also have to consider this case. The same is, and to approach this, we expand the determinant again. And by a rearrangement, we know that fxx fyy is equal to fxy of AB squared and is non-negative. But fxx of AB plus fyy of AB is equal to 0. So fyy of AB is equal to minus fxx of AB. So we have minus of fxx AB squared is non-negative. And this must imply fxab is 0, and it is a contradiction because fxx is non-negative on R squared. And on the other hand, we may assume that f has a local maximum, but this is quite similar with the local minimum case. We can just repeat the same process, so we don't have to do this again. You can do this on your own. And because all cases lead to contradictions, f has no local maximum and no local minimum. And we're done. Let's move to B. We have to show that f is not constant on the unit circle. And in fact, f is not constant on all circles centered at the origin. And to show that, we may assume that fxy is equal to some function. We will g of x squared plus y squared, because if x squared plus y squared is 1, then fxy is a constant. And here we assume g is a C2 function, so that we can compute partial derivatives up to the second order without any problem. So from fxy is equal to g of x squared plus y squared, we compute the partial derivatives using a chain rule. So first we have fx equal to 2x times g prime of x squared plus y squared. The same is y. You have to be familiar with chain rules. So now we have fx, fy, fxx, and fyy. Now we compute fxx plus fyy. This is equal to 4 times g prime of x squared plus y squared times 4 times x squared plus y squared g double prime of x squared plus y squared. Then on the unit circle, we have fxx plus fyy is equal to 4 times g prime of 1 plus 4 times g double prime of 1, and it is equal to 0. So by rearrangement, we have g double prime of 1 is equal to negative g times g prime of 1. Now we consider fxx. fxx is now 2 times g prime of 1 plus 4x squared of minus g prime of 1, which means it's 2 minus 4x squared times g prime of 1. Therefore, at 1 over plus or minus 1 over square root of 2 plus minus 1 over square root of 2. At these 4 points, we have fxx is equal to 0, because 2 minus 4 times 1 over square root of 2 squared is 0. So it is a contradiction. And that's the end of problem B.